So today we have the absolute pleasure of being joined by Michael from the Firedancer team to help explain this incredible dashboard that they have built. As some of you might know, our super team and staking facilities validator has been the first, besides obviously the Firedancer's team, to launch Firedancer on mainnet. And we're going to learn a little bit more about what they built and what their incredible dashboard is actually trying to tell us. So, Michael, would you like to say hi?
Hey, yeah, thanks, Rebecca. I'm Michael, one of the developers here on the Firedancer team. Mostly I'm helping just get everything shipped, make sure we get it all out into production. And, I kind of a little bit responsible for this GUI we built as well.
Amazing. So the idea for today is just to have a little bit of a run through of everything that is going on here. There are an incredible number of moving parts, and to have a little bit of an overview, and especially in 10 seconds, if you want to tell us what is going to happen.
Yeah, so we're about to be the leader on the network. So it's interesting to see. You'll see a bunch of movement in the interface here. And there it goes. We'll come back a bit later and talk a bunch more about like what's going on there and what's happening. I guess I wanted to start a little by talking about like why we built the interface and who it's for.
Yeah, absolutely. Please.
Now, I would say there's kind of three key constituencies here. The first one is really the developers. This is anyone that's contributing to the core validator software, the Firedancer development team, potentially if there's other validators, ANZA. So useful as a developer to be able to see what's going on inside the validator, especially as we're diagnosing issues and want to be able to fix things quickly, iterate really quickly on the software, and ship things quickly. Having this kind of ability to look inside is really, really useful. The second constituency, is the end users. There's like app developers and people that are working on the chain. I think allowing them to also see the same thing, visualize what's happening, send a transaction and see it actually arrive at that validator is very useful. The third one, though, and probably the one, the main user, I think, here is the validator operators themselves. Validator operators is kind of a little bit forgotten about, and sometimes they chew a lot of glass, as the community likes to say, right? It's a very tough job to be a validator. And so, when we have them, we really want them to run our software as we're building Firedancer. It's, I don't know, the GUI is like something of a sweet treat for them, right? It's a little bit of dessert. It's like, here's something that hopefully makes your life a lot easier and can get you really comfortable with running Firedancer and Firedancer, right? We need them to understand the system really well to be able to run it. We're building this software, but we don't operate it. So it's partly an education tool to help them operate the software really well and make sure it's running as fast as it can. And we'll see some of the ways it highlights, ways it's not fast, or it could be not fast if it's not configured properly. So those are kind of some of the main reasons we're building this. Another, it's kind of also just a shot in the dark, right? Sometimes you build something and see if it's useful. And so this is the first iteration of it. I think we're learning a lot from it, and it has proven to be somewhat useful. And so, our plan is to expand it a bunch more, add a bunch more functionality here as we build out the full validator software.
Yeah, amazing. And I think especially if it's helpful for you to help also understand what's going on internally, but also if it benefits the other validators and kind of understanding what's going on behind the scenes in a very helpful visual way. And you've also built in a lot of really interesting interactive parts. So I know it's not absolutely the last iteration of your beautiful GUI, but we would love to get a little bit of an overview of what you've created. Maybe starting at the top and your little epoch slider, maybe.
Yeah, and we'll walk through kind of all of the elements here, I suppose, one by one and just describe them. So the first thing you'll see here is the network that validator is running on. This could be mainnet, it could be testnet if the validator is on testnet, it could be development, devnet. We've kind of picked these colors to indicate what network you're on, so it's really easy to see. In this case, this validator is running live on mainnet. We're showing the software version here of the validator. This is a Firedancer build, I think running off the main branch. Up here, you can select a few different views. We'll click on them pretty quickly, but the main view we'll talk about right now is this overview page. And in the top right is kind of some general validator information. So the validator name here is the identity of the validator. This is a public key. Kind of just the validator is how it connects to the network, how people identify it. It's this long sequence of characters and digits. The stake amount, we're showing this is the amount that stakers have delegated to that validator on their behalf. Here we see that the validator we're running has about 1.4 million SOL, and we show that as a percentage of the network's total stake. So this is 0.36% of, it's about 1/300th of the entire stake that's staked on the network. We then have the uptime of the validator. This is, a standard, like how long the validator's been running without being rebooted, which is almost 2 days. And the commission rate, which is what percentage of the inflation rewards that the validator owns are kept by the validator versus being returned to the stakers who delegated to that validator. Continuing kind of down with the UI, and feel free to stop me if anything here is not clear. We're showing the epoch. So epochs in Solana, a little hard to describe, I think, without the GUI. Still tricky with the GUI, but the Solana network, the way it makes forward progress is each one of these validators has a chance to produce blocks. And so, each validator is producing blocks. They'll produce 4 in a row. The blocks are grouped into big chunks called epochs. So there's about 432,000 blocks in an epoch. And that's kind of an arbitrary choice of the network, but it's used to select the leader schedule. So once every epoch ends, all of the validators kind of come together and agree what the leader schedule should be for the next epoch, which is who gets to produce blocks in what order. The interesting thing here is we're showing our leader blocks on this little timeline. So this epoch timeline we have here is a pretty cool way to navigate through the application. So you'll see we can drag this slider around, and this is going to navigate through the epoch. You'll see down here, we're kind of moving around the different slots. We actually have a leader slot coming up here again. So if you look down the bottom, you'll see us receiving a bunch of transactions. We're going to try and produce a block. And here it's done its job properly. You can come and look, we produced a block. We'll talk about this again when we get back to it. But for now, we'll go back to the leader schedule. So this slider is really showing the entire epoch, and all these bits that are colored kind of a lighter blue when we were the leader. There's these little red icons kind of all over the place, and this is when we were the leader, but we skipped our slot. So we didn't actually produce a block that was included by the network. We can also talk a bit later about why that happens and how we can diagnose the issues when that's happening. So yeah, this is kind of the current epoch. We're in epoch 700, and yeah, I think that's kind of most of the components at the top there. We kind of keep going. Then we have this general status information. So this is the slot number. The network just advances one by one. So as each leader validator is producing a block, this number is incrementing. This is kind of showing also that our validator is live, it's working, it's healthy. Excuse me. And we're voting, right? So when leaders in the network produce blocks, all of the other validators are required to vote on those blocks, whether they replay it successfully, whether they think it's valid, whether it should be included in the network. And what we want to see is that our validator is voting without a lot of lag. So very quickly after a block is produced, we should be voting on it. Typically, you'll see this be 1 or 2. The smallest number you'll see here is 1. We can't vote on a block inside that block itself. So, the earliest it could happen is the very next block. Sometimes it'll increase a little bit if there's network jitter, we're dropping traffic, or our validator is, a little bit slowed down because of the operating system or some disk issue. But typically, if we're healthy, this would be quite close to 1. Now we're showing the time until we become the leader. So this is when we next have an opportunity to produce a block for the network. You'll see we have a lot of leader opportunities on this validator. This is because it's staked so highly. So in Solana, the amount of leader slots you get is proportional to your stake percentage. If we were to have, say, 10% of the stake of the network, no validator has that amount, but we would probably be getting leader slots very, very regularly, every few seconds or every 20 to 30 seconds. If we, on the flip side, had a very low amount of stake, let's say 0.001, we may only see 2 or 3 leader slots in an entire epoch. So this validator is getting them quite regularly, which is why we get to see all these slots happen. And here we're just showing what the number of the next leader slot actually is. Moving to the right, we have the transactions view. This is showing the transactions per second that are happening on the network. So we have the total TPS. This number is an average over the previous 10 seconds. So you can see it's kind of a little bit smooth, but it moves up and down. And again, all the numbers here are completely live streamed, absolutely real time, almost no latency from the actual validator software itself. You can see the network right now is doing, between 3,500 and 4,500 transactions a second. In Solana, the way validators vote is they send a transaction to the leader. So the votes themselves are transactions that get included in blocks. So a lot of the TPS is taken up by votes. They're very easy to execute, so they don't consume a lot of resources for the network. But yeah, we have about 3,000 of this TPS is just votes. So that's the part of the chart in blue. So of the non-votes, there's two other cases. There's non-votes that succeed, which are transactions that didn't run into an error. And there's non-votes that fail, which are real transactions that hit an error. Often because the program tried to do something, divided by zero, or it did something illegal. It failed. These transactions that fail still get included on the chain because we want the person who sent the transaction to still pay fees. They cause the network to do a lot of work to run the transaction. And so these red transactions are actually still being included, they're being processed, but they don't, if it's a transfer, the transfer doesn't succeed. So the sum of these three, the transactions that are succeeding, the transactions that are failing, and the votes gives us the total TPS of the network. Moving further to the right, we have the validators section here. Solana mainnet is pretty diverse. So you can see there's 1,450 different validator computers around the world that are part of this network. These are different machines running in different data centers and different, geographic locations, potentially on different networks. And the stake is split between these validators in something of a power distribution, right? The biggest validators have, in some cases 2 or 3% stake, although there's really only a handful of them. And then there's a really long tail of validators that have a bit less, 0.5 or 0.36 as our validator does, or much, much less in some cases. Pardon me. So yeah, there's a large set of validators. They're all sharing leader slots. So as the network progresses, each of these validators gets turns to produce blocks. We're showing here the total amount of stake that is non-delinquent. And so this is this kind of blue amount. A delinquent validator is one, usually what it means is they're offline. The way this is determined is, recall that all the validators have to vote on every block, and we're showing here how far behind our validator is on voting. If our validator, computer has let's say a power failure and it switches off, we're going to stop voting. The network won't be able to see any traffic coming from our machine. And once we haven't voted for 150 slots, 150 of these blocks that are getting produced, the network is going to consider us delinquent. And so you can see there's a very, very small percentage of the stake is currently delinquent. This means the network's very healthy. Almost none of the machines are offline. As well as being offline, there are other cases where validators can go delinquent. One case is if the validator is said to be falling behind. So a validator's job is to replay the blocks that are produced by the leaders and verify that they're valid and accurate, that nobody tried to send a balance of SOL that they didn't have, would be one example. If a validator isn't able to keep up in doing this job, maybe the network is producing transactions too quickly and their computer is a little bit too slow, they may start falling behind the network. And once they've fallen behind more than 150 slots, they will also be considered delinquent. And again, this is an important number to track because it's kind of reflecting the health of the set of validators, right? I think here we're showing, the mainnet is very, very healthy right now. The RPC nodes are a bit different from validators. So they run the same software. They're still receiving all the transactions from the network and replaying them. But the main difference is they don't get a chance to produce blocks. So these nodes are not staked. They have no SOL delegated to them. The reason someone would run one of these is they want to listen to the transactions to, let's say, produce a website, right? Maybe they want to show some information about the network as it's happening. Maybe they want to show some data. Maybe they want to, build a distributed app or decentralized exchange. So they're going to need to learn what's happening on the network and listen to all its information. But they don't necessarily need to be staked or actually producing blocks for that to happen. So here we can see there's about 3,215 active RPC nodes listening in and providing data to all the applications that power the Solana ecosystem. Anything you want to cover a bit more of there, or we can keep going?
No, I think it's good. Although I did have a question, because do you have a GUI that also what you can look at the different testnets? I assume it's the same little block with all the mainnet validators, right? Or is it when you switch into the testnet, does it actually say the number of testnet validators rather than mainnet?
Yeah, no, it'll reflect that specific validator. I don't know if I have it available to pull up, but if we were showing this for testnet, it would actually have the information specific to testnet. So it would show, I think testnet actually has about 3,000 validators and a much lower amount of RPC nodes. So it would show very different numbers for testnet.
Okay, very cool.
All right, we'll keep going down, and hopefully within the next 4 minutes, we'll understand this TPU waterfall enough to see what's happening during the leader slot. So each leader gets a chance to produce a block periodically. The blocks, you can see the slot counter is going up here somewhat quickly. It's targeted to increase every 400 milliseconds. This number should go up. So each leader has 400 milliseconds to produce their block. Sometimes it stops for a little if a leader takes a little longer, or maybe they're a little quicker, but in general, we expect it to be about 400 milliseconds. Pardon me. So our leader is next scheduled to have a 400 millisecond turn in about a little over 3 minutes. And what we're showing with this TPU waterfall is when we have that 400 milliseconds, what we're doing as the leader is we're taking all these transactions that users have sent us, or RPC nodes, or anybody on the network has sent us, and we're going to try and put them into a block in a very smart way. What the validator is kind of doing is it's taking all of the transactions and it's ranking them. It's deciding which ones are going to produce the most revenue, the most fees for the network, and have the highest economic utility. So it's essentially kind of looking at how profitable would this transaction be to include. I want to pick transactions that are, have a high fee, meaning the user wants them to go onto the chain quicker than, say, some other user wants a different transaction to go on, but also are low in compute use. So the ratio between these two is, kind of the profitability of the transaction will determine how highly it gets ranked. So what this waterfall is showing really is the path of transactions that we've received from all the way from the network through to whether they make it into a block. Right now, we're not leader. And I think a big point of confusion people have with this interface is they see that we are receiving a lot of transactions here, but nothing is making it into the block. And if you click this % button, what you'll see is, nothing has really made it into an actual block yet. This is because we're not leader. We're just kind of sitting here and building up our transaction buffer for when we are leader. But even the things that we've actually made it all the way to being stored so that we could put them in a block when we're leader is very small. That's this number here, buffered. I think this is a bit of a surprising thing to people, but it is reflecting the reality of the network, which is that a lot of transactions that are received by the validator are duplicates or not useful or not able to be put in. So the validator is really doing a lot of work here to actually produce a block. And so we'll walk through this at a bit of a high level. So here we're receiving transactions from the network. There's a few ways you can receive transactions. Mostly they're coming in via what's called QUIC, which is a network protocol. It's a little bit like TCP, if you're familiar, but supposedly a little bit faster. We can also receive transactions just over UDP itself. And what this is showing is, okay, we've received about a million transactions since we were last leader. Always this diagram is kind of showing what happened since we were last leader. So since we produced our last block, we've received 1.1 million transactions. And then we're showing, what happened to these transactions, right? This is called a Sankey diagram. There's a lot of them like float around on Reddit and things, but here you'll see, okay, some of the transactions were malformed. That means they didn't look like a transaction. We couldn't recognize it as a transaction, so we threw it out. Sometimes they're aborted, right? Which means the connection, the client sending us the transaction stopped halfway through and they disconnected. if they make it through this initial part of the system, which is our server that's receiving the transactions from the client, then they go through some other stages here, right? They're getting verified. So we're checking that the signature is valid, that the user that's sending Sol actually is in possession of the key and they signed the transaction so that the transaction can actually be performed. We're checking that it's not a duplicate. And so if we look really quickly, we're about to become leader. What we're doing is buffering all these transactions. And then as we're leader, this buffer will drain and we're going to start putting some of those transactions into blocks. And you'll see we were still receiving a lot of transactions as we were leader. So the buffer didn't drain a lot. Pardon me, but this waterfall has another kind of cool feature where we show those slots that have already happened. We'll do that just once we get to the end of this waterfall and see some of the other cases things are failing. So duplicates are another big reason. A lot of transactions that are sent to the validator multiple times. You can imagine if you really want your transaction to go through, you might try sending it 5 or 10 times. So the validator is just going to filter all of those duplicates out. So only one copy makes it through. There's some very unique cases here, bad LUT. This is kind of like a malformed transaction. It's referencing a special kind of instruction, a lookup table on Solana, and we couldn't find the lookup table, or there was an error with the lookup table. Finally, we get to pack. Expired is really the main thing that can happen to transactions here. And Solana transactions have a lifetime of about, somewhere between 1 and 2 minutes. So if you send a transaction and we're not going to be leader for the next 2 minutes, there's no way that transaction would still be eligible for inclusion by the time we become leader. And so we expire those transactions and throw them away. So this is kind of one of the main reasons the buffer amount, the amount that are actually available and ready to be put into a block, is always so low, because a very big majority of the transactions we're receiving are outside of the window of when we're going to be leader. Sometimes the buffer becomes full and we're going to drop the least profitable transactions because they would have no chance of making it into the block when we became leader. Anyway, then there's this unpackable case, which is very, very technical, but is sometimes transactions would never be eligible to be put into a block anyway. One case is if they request so many resources from the network that they could never feasibly execute. Another case is if they're locking accounts, locking certain system reserved accounts that they shouldn't be. So this is kind of the lifetime of a transaction, right? It's been received from the network, and it's a kind of a Herculean feat for the transactions to pass through all of these checks and make it all the way into the buffer to be ready to be put into a block. And here you can see, we have about 0.4% of the transactions actually made it that far. So now we can kind of ask the question, well, what happens when we become leader? How do we put them into a block? And so that's what you see when we become leader. We kind of flash the diagram here. Some of the paths grow and some of them shrink really quickly. What's really happening is this buffer is draining out into the block. And so that's why we have all the different slots here. These are our leader slots that we've had in the past. And we can go and view for what happened in the past, how are we behaving? So let's take these last 4 leader slots we looked at. Here is one 716 it's ending in. And so this is the transaction waterfall for the time period leading up to this leader slot. So you can see there's a lot of failures, a lot of things going wrong. But in the end, what we're kind of looking for, and we can kind of click through some of these leader slots here, what we're looking for is transactions to actually make it into this packed state. So they made it into a block. So when we become leader, we send transactions a little bit further through the pipeline. They get packed and put into a block, and then they either fail or succeed. Some transactions, we try and pack them, and they aren't able to execute for some reason. Usually, this is because the transaction already executed in a prior block from a different leader, and we didn't realize. But yeah, so you'll see in this block, we've put 2,086 successful and 45 failed transactions into the block. Here we have some info on the top right, a bit more information about the block. We put 1,880 vote transactions into the block, 250 non-vote transactions, and we consumed 26.6 million compute units. Now in Solana, each block is constrained to be at most 48 million compute units. This is to prevent a malicious party from overwhelming the network by sending really, really big blocks out when they're leader. that no one would be able to verify in time of the 400 milliseconds. So here we've produced a somewhat full block. In general, we should aim to have all of our blocks completely full. This is going to totally saturate the network. Firedancer is still a little bit in development, so we're ironing out some issues to make sure our blocks are always completely full. And here you can see the fees we've earned on this set of transactions we put in the block. So as we talked about, to get highly ranked in the buffer and make it into a block, transactions will a little bit have to compete and pay higher fees depending on the congestion of the network at the time. And so all of those fees get collected by the validator. Half of them get burned currently and half of them actually get returned to the validator itself. So here you can see we've made about 0.4 of a sol of priority fees. Then there's always a much, much lower amount of transaction fees, which is just a baseline fee users pay to get the transaction included as well. So we can kind of click through some of our previous leader slots and see, here we did a very good job. We've put a roughly 48 million compute unit block onto the network. This one had a lot of non-votes and only a few votes. So this is kind of this waterfall component, at least seeing how the transactions move through the network. It's a very kind of counterintuitive thing, I think. A lot of people view this and it's a bit surprising at first, but the more you get to understand the network, the more it makes sense. And I find it's like a little, in some way, like a beauty to the data here, right? This is showing like real economic value being created right now as it happens. Like these are real users trying to send real transactions, and our validator is going to put them into a block and actually make that transaction real for somebody. If we kind of keep going, just to finish off this page, down the bottom we have what I would call like CPU busy indicators, right? If you ever had gone to your task manager on Windows and you see like your CPU cores going up and down, that's pretty much what we're showing here. Except it's CPU cores as they're used by our validator software. So the validator software is composed of a bunch of different tasks. And probably the simplest way to illustrate that is just to describe a couple of the tasks. So one of them is verify. We talked about that a bit before. One thing a validator has to do is verify that users that are trying to send transactions actually possess the key that owns the account that is trying to do the transfer. So if I own some account with a bunch of Sol in it and I want to send it to you, I have to sign that transaction with my key so that the validator can verify that I really have permission to do that. And so this verify part of the system are CPU cores that are dedicated to just verifying transactions were valid, that the person was in possession of the key. And you can see here we have 6 CPU cores of the system dedicated to this job. They're relatively unbothered. So this 0%, it means what it says here. The cores are just almost idle. They don't have a lot of work to do. And you might wonder, well, if they don't have a lot of work, why did we have 6 CPU cores here? The work can increase. It's very variable. Right now, we're not leader for another 9.5 minutes. So we don't expect anyone to be sending us a lot of transactions. And that's kind of the case. You can see we're getting a pretty slow trickle here. If we become leader, we may expect a lot more transactions to be getting sent. And you can view that when we click on these past slots. These busy diagrams are going to show what the CPU cores were doing during that leader slot. So this is representing about a 400 millisecond period. You'll see that in some of these slots, it's a little bit higher. This one here in particular, most of the cores were about 36% busy throughout the slot. Here, about 26%. So in general, we try and set these amount of cores allocated to a specific job so that it's never overwhelmed, right? It would be bad if we got so many transactions that we couldn't verify them in time, and then we might drop transactions and lose them. And that's bad for the users. A user, if maybe that was a really valuable transaction, a huge amount of economic value was going to be created from it, and we lost it. So this verify job is quite expensive. That's why we have so many cores dedicated to it. We kind of talk through the other jobs here. We have networking, which is receiving transactions right off the network. It's kind of communicating with your network card in the validator machine. We have quick, which is talking the network protocol to the RPC or the user that's sending the transaction. So this is kind of actually serving the user and making sure we receive all their bytes correctly and that we can pass them on to the rest of the system. Dedupe is doing this duplication check and making sure that there's no duplicates and just filtering them out. Resolve is a little tricky. It's mostly checking that the lookup tables are valid. So if you have an address lookup table in your transaction, it's referencing some on-chain data to figure out which accounts can be used in the transaction. So we're just resolving those accounts and making sure they're valid here. Pack is kind of the central, I would say, heartbeat of the system. This is the main place the magic is happening, which is really when we become leader, it's deciding what goes into the block. It's ranking all these transactions, it's going through them, it's picking the best ones. So you'll see most of these are idle really because we're not leader. All of these CPU cores really only get activated when we're about to become leader and when we're actually producing a block. So Pack, once it's figured out what transactions to put in, it sends them to these so-called banks. These are really just execution CPU cores. So these are actually executing the transactions, figuring out what the result was. Do I need to send this SOL to this account? Do I need to write this data into this account? Things like that. POH is a curious one. You might look at it and say, oh, well, we're not leader. It seems very busy. It's always at 90%. This is kind of part of how the Solana network is secured. It's called the proof of history mechanism. I won't describe it in full detail here, but this is always running in the background producing hashes. And the idea here is our validator is always ready to step in as leader if the leaders that were before us are offline. So we always need to be computing hashes on their behalf just in case they don't produce a block. And so that's why this component is running here very, very busy. Shred is the part of the system responsible for sending block data between validators. So when we produce a block, we have to send it out to the rest of the network so they can validate it. The way this happens is we don't send it to all 1,500 validators. That would be very expensive and slow. So we produce the block and we send it to a handful of them, maybe 2 or 3. And then those 2 or 3 validators take the data we sent them and they forward it on to some other validators. And it kind of fans out in this tree fashion where each validator is sending the data on to some other validators. And this lets us send all the data to all of the validators in the network so they can verify it very, very quickly without us having to, send 1,500 copies of it, which would take a very long time. And so you'll see, even when we're not leader, the shred tile is kind of busy at times. And what this is reflecting is we're receiving blocks from other leaders, right? They're producing slots here as the network moves forward. And we're receiving that data from some other leader, and we're going to have to forward it on to a handful of leaders ourselves. And so we validate it, we check where it came from, we figure out who we need to send it to, and we send it. And that's why it's quite variable. Sometimes, we don't receive a slot for a little bit. Sometimes we receive a bunch of data for a block all at once. But this is the main job of the shred tile. Then we have the storage CPU core. This is just taking all the data we've received that represents all of these blocks and storing it on the disk. Again, this is quite idle because we're not leader. And then we have the networking CPU cores that are on the outbound side. So they're sending data out rather than receiving it in. A few of these CPU cores have little info boxes here, and these are just little pieces of data relevant to that specific job that you might be interested in. So on the networking inside here, we have the ingress bandwidth currently around 70 megabits a second. Although if you look when we're leader, the bandwidth is much, much higher. Here, when we've had a leader slot, we've almost done a gigabit of inbound traffic. So this is a gigabit of transactions being received. A lot of volume there. You can see in this leader slot, we also had about 33,000 quick connections. So this is actually 33,000 RPC nodes they might be, or users or apps or anything that's connected to our validator and sending us transactions. And then verify and dedupe are kind of what they say, just how many transactions were, what percentage of transactions failed verification or failed deduplication. This percentage is a little, it's representing how many failed and how many were duplicates at the verify stage. So if you look, we have the 6 verify cores. Each of these individual CPU cores is also checking for duplicates. And then they all get consolidated onto one CPU core that checks for duplicates that may have been on different of these CPUs. So that's why there's this 2-step deduplication. And if you look in this slot, we had a lot of duplicates. So that's where most of the failures are coming from, but almost no bad signatures. Users generally send well-formed and validly signed transactions. So we only had 31 that were thrown out due to a bad signature. Pack full is how full the buffer is of this packing system. So once it gets to 100%, it's going to have to start dropping. But again, the dropping doesn't matter very much here because the transactions would never make it into a block if they're not, in the most 65,000 valuable transactions at this point. And the bank here is just showing what the TPS throughput of each of the bank's CPU cores is. So here it's about 2,000, although you can see that the banks are not very busy. So the actual, if they were saturated, the actual practical throughput would be much, much higher. All right, that was a lot.
That was amazing. Thank you so much for walking us through. I'd be curious. So you've obviously these are the pieces that you've chosen to add in first, and that have potentially then found it the most important aspects to track. Is there anything that you feel is missing, or that you're wanting to continue adding on or changing in the future?
Yeah, I think one thing to note with this system is it's mostly reflecting information we have available in Firedancer. So Firedancer is our initial hybrid validator, right? That's using parts of Agave, like the consensus components. And then here we've, pulled in our entire networking stack so we can try and produce blocks really quickly and really effectively. So we have these 2 jobs of the validator, right? There's the producing blocks when you're leader, and there's validating other people's blocks when you're not leader. We're not showing a lot of information here about the validation process. And that's because all of that validation still is happening in the Agave components of the validator. So it's a little trickier for us to wire that up and deal with it with this system. And the Agave validator is really responsible for a lot of things still, like gossip, would be one example. Repair is another example, when we fetch data, when we didn't receive it in real time, maybe there was some network jitter. So there's several kind of components here that really aren't represented so well that we hope to be adding as we kind of move to a full Firedancer that is re-implementing those pieces as well.
Amazing. It looks like we're going to get another leader slot, which is so exciting because our validator, we get much, much fewer leader slots. And so it's really been exciting to sort of see the process, and especially going through and explaining all the different pieces so that you can actually really understand all of the movement and happening, because it happens so quickly too, right?
Right. Yeah, we're trying to kind of show, here we'll have the leader slot in 2 seconds. We're really trying to show things real time, right? We want to show you how fast this validator is actually moving when it's leader. Oh, and here's a really interesting case. We skipped a slot. So that's something we hadn't seen before, but here you'll see that the blocks came out red. So they were skipped. The network didn't choose to include the blocks we produced on the chain, and so these transactions didn't land. If we move over to the leader schedule page, if you didn't have other questions, we can go through the leader schedule page and really talk about this case where we skip leader slots and why that happens too.
Yeah, we need to know now.
Right, and you'll see we have a few of them that have happened up here, so we just added a new one onto our timeline. And leader slots, skipping leader slots is generally not good, right? It's not ideal. It's time that the network wasted a little bit, right? There was a 400 millisecond, or there were 4 of them, 400 millisecond chunks here that we weren't able to process any transaction. And so here we'll come to the second page of the validator, the leader schedule. If you're unfamiliar with how Solana works, this is probably, I would say, just stare at this page for about 5 minutes and your amount of knowledge will increase dramatically as you try and just understand what's going on. And so here we can kind of just do that. And I'll try and explain what's happening. And so this is actually viewing the leader schedule of the network as it moves through the slots. And so this is, again, real time. Each time one of these little green dots comes out, that means a slot was produced by the leader that you're seeing on the left. You might say, well, why are they kind of grouped together like this? This is actually part of the design of how Solana works. So we want slots to be 400 milliseconds, but we don't want to change the leader computer every 400 milliseconds. Because, what if the leader computer A was in Europe and leader computer B was in Asia and leader computer C was in America? Every time we switched leader every 400 milliseconds, we'd have to make sure all the data moved from A to B to C. And so there'd be a lot of latency. And so what the designers of the network here have done is said, okay, we'll give each leader a group of slots in a row. Every time you get to be leader, you'll get, instead of having one, you'll get 4. And so that's why on the overview page, you'll see all of our leader slots are in groups of 4. And on the leader schedule here, they're happening in groups of 4 as well. So as we're moving through the network, each leader is getting their turn. They have 400 milliseconds for each of their slots. So they have 1.6 seconds as leader total to produce blocks. And then they're going to hand the leader roll off to this next computer, which you can see are getting scrolled in from the top. In general, you'll see the slots take about 400 milliseconds. So that's this duration field here showing how long it took us to receive and replay. There's quite a bit of jitter. A lot of this is due to the network. Maybe we received some data a little slower, maybe then the next data came a little quicker. But on average, it's a little bit, just a hair over 400 milliseconds. Occasionally, I think we saw one a little second ago, you'll see a slot get skipped, like what happened to us a minute or two ago. And what that means really, in very rare cases, almost never, here is one that just skipped. Almost never, what it means is that that leader produced a bad block. So they produced a block that had something invalid in it. This is very rare. It would require a software bug or a malicious leader. And the network's pretty good at just throwing those away. Really, what's much more common is that the computer was just offline. So the power cable got unplugged or they were restarting the validator. And so it just didn't produce anything. And the network says, oh, they didn't produce anything. We'll have to skip those leader slots. No one else can step in and produce data there. The much more interesting case, though, outside of those two is when the computer is online and tries to produce a block and the block is valid, but it gets skipped. And the main reason for this is that the computer was, I don't want to say slow, but often it's that the network was slow, right? Let's say that we are the leader, this validator right, that we're looking at. So we have 1.6 seconds to produce all 4 of these leader slots and send them to this next validator. And if we don't get it sent in that amount of time, the computer after us is going to say, oh, well, they were too slow. Maybe they're offline. Maybe they, crashed in the middle of the slot. Maybe this data is never going to arrive. They're sort of under an obligation to just start their turn at some point. And so that's what happens. And they'll wait. They'll give you a little bit of a grace period. But to make sure that they don't take too long to produce their block and they don't wait for you forever, at some point they've got to cut you off. So the majority case where these skips happen tend to be just because the network was having, the network between those two computers was having an issue and the data couldn't be handed off in time. And if you look at the slot we skipped, often we can try and understand if that is what happened here. So you'll see the network was definitely not performing well in the lead up to our slot, right? Here we took 1.2 seconds to replay this block rather than 400 milliseconds. And here we're taking almost a second for each of these slots. And you can imagine as our computer here is taking almost a second for each of these, what should be 400 millisecond blocks, we're falling behind the real head of the network, right? We're falling further and further behind. And by the time we've got to our slot here, what happened is our leader was perhaps 2 seconds behind. And so we didn't start our block on time. We didn't finish it within 2 or so seconds. And so the leader after us just didn't think we were going to finish. And they waited a good amount of time and just went ahead and produced a block without us. And the rest of the network voted on that and agreed that we should have, that we lost. It's generally pretty rare. You can see up here, we're showing the skip rate of our validator. So it's 3%. This is always something we're looking to improve. And we're generally the development team of Firedancer and Firedancer. We look at almost all of these skip slot cases and try and determine if it was something preventable or if it was a bug. So as a validator operator, it's kind of fun to come in here and really try and see, why did I skip? Here's another case where we skipped quite a while ago. And this one is very obvious, right? The leader ahead of us, we thought that they were asleep, right? We didn't see this block for a long time, almost 2 seconds. So we just went ahead without them. And then as we were going and building some of our blocks, they actually published it. They came out and said, oh, whoops, I was late, but here's my block. And the networks just happened to accept what they published over us. Probably they got their data out to more people more quickly, and it was voted on. So in general, here's another case. Again, same thing. The leader in front of us, we thought they were slow. They ended up publishing right after we decided to skip them. Here, a few leaders before us skipped, and so we were probably quite confused about who to build on top of, and ended up getting skipped also. Here is also a kind of interesting case. You might look here and see, wait, we replayed in 70 milliseconds. How does that happen? Shouldn't it be 400? What's happened is down here. One of these blocks either was really large or really slow, or we had, maybe our disk locked up, and we took, 4.5 seconds to replay this block. And so we've fallen behind, and now we're trying to catch up really quickly, right? Our validator is 4 seconds behind the network. So we're playing really quickly, trying to catch up. And it looks like we didn't make it because, we produced a block here, but the validator behind us didn't see it in time and went ahead and skipped us. So that's kind of the mechanics of skipping. Again, not anything malicious. It's a little bit expected just because of network jitter and things like that. But, we're always trying to get this down. And hopefully for the validator operators, this is a really useful tool to help them figure out why they're skipping and, help us drive this rate, hopefully down to 0 at some point. A few other things that are interesting on this page. You'll see these little green circles here. They start off empty and very quickly get filled in solid. This is reflecting the slots being optimistically confirmed by the network. So when a slot is first produced, it's somewhat not immediately able to be trusted, right? Let's say I'm a merchant and I'm selling shoes, and you send me sol, and it gets included in a block. I shouldn't probably ship you the shoes the second I see that block because, go drop them in my mailbox 400 milliseconds after, because there's a chance you might get skipped, right? We were talking about all these skips. There's a chance that block may actually get skipped and it won't be included and you'll never receive the sol. And so what you want to know sometimes as a merchant or as someone in the ecosystem is, well, when can I go and do that action, right? When can I drop the shoes in the mailbox? So Solana has this concept of optimistic confirmation. And that's happening as these circles get filled in with the solid green here. It's just very, very quickly. I mean, usually less than 400 milliseconds, sometimes 100 milliseconds after the slot completes. What this is saying is that 2/3 of the network have, I believe it's 2/3 of the network have voted that that block is valid. So it's very unlikely to be undone. And this is kind of a safe point to say, okay, the transaction is relatively confirmed. Now, if you want to be extra safe, maybe you're, buying a large company and you're transferring a lot of money, what you want to wait for is the slot to become rooted, which means it cannot be undone. And if you scroll down a bit, you'll see slots getting rooted a little bit after they get produced. This is the network kind of waiting a second and saying, okay, let's make sure it's really not going to fork and that everybody agrees on it. So slots get rooted once they've been confirmed, and there's 31 slots have been put on top of it. So this rooting process typically takes somewhere in the order of like 10 to 15 seconds, but it can be a little longer if the network isn't agreeing. So that's kind of this column with the check mark that turns into the rooted, and you'll see the skip slots here have this little skip icon. We have the votes and non-votes that were included in the blocks. This is what the leader decided to put in there. How many fees they've earned. You can hover over this to see the breakdown between the transaction and priority fees. In general, you see, leaders making, right now the network is very busy. There's a lot of activity happening. And so you'll see that fees are actually a little higher than they usually are. The duration, which we talked about quite a bit, and the compute units, which we also mentioned earlier. Here you'll see it's going to show 100% if the block actually got filled. In general, so we're looking at mostly agave validators here. The network is almost entirely comprised of agave validators right now. So the compute units they're putting in, sometimes are 100, sometimes a little less. If we look at just our validator by clicking this My Slots button up here, what this is doing is just filtering this whole leader schedule to only show our own validator. And you'll see us produce a block in this page here in 3 seconds. Yeah. 2, 1. Here we go. Now we just produce a block, and you'll watch it actually get rooted here in real time in a second. Luckily, we did not skip this block. So it's been 12 seconds, 13, 14, 15, there it goes. If we scroll down, you'll see roughly half full. So a lot of the time we're packing very, very good blocks, right? 100% compute units, we're earning a good amount of fees. And so that's kind of what we're tracking as developers, is making sure that your blocks are always full and that they don't skip. Those are really the 2 primary metrics that the development team has to make sure the network is healthy. I believe we kind of covered most of this page. One other thing here is you can filter just to your skip slot. This is kind of useful to see what you've been skipping, although again, you can click these little red kind of caution signs up here to see them. You can also click on this actual slots themselves on this timeline to jump to that specific slot that you built. And finally, there's this search bar here where you can kind of filter different slots or different validators. I think, we can put in a name of a validator and see just here I'll pick Helios just because they're the largest by stake right now. So we can see all of Helios's leader slots, whether they skipped or not. Yeah, they skipped 1. We can also see their upcoming leader slots in the future. And we can scroll this epoch timeline around like we could on the overview page to kind of navigate all of the data in this epoch. We can click this resume real-time button up here, which I forgot to mention. It kind of jumps back to the current time. Yeah, I kind of think that's most of the leader schedule page now too. Hopefully you're still with me.
No, absolutely. It's incredible how much detail you've built into this, and it works as a really incredible diagnostic tool, not just for people, your own validator, but to also kind of compare and contrast and see what's going on in terms of if it's Firedancer or Agave or what's actually running behind the scenes. And it's really interesting to see because, for example, our validator, we don't have any skip slots. And so we also have much fewer leader slots. And so it's really interesting to also kind of compare what our different, stats are looking like, and also potentially, for people like Matthias, also understand and be able to refine, because we're one of the very few Firedancer validators, and to see how it's performing, especially since it's so new, right?
Right. Yeah. Awesome. I'm glad you're finding it useful. We're certainly open to all feedback too, especially from the validator community. If there's things that you think would be super useful to see in here, or ideas you have for what you want, what you want to see, we're very open to that.
I think too, it's such an incredible tool for just education, because it's very rare you can actually see the blockchain working in real time. And I think one of my last questions, and then I'll tell Matthias if you have any questions too. I'd be really curious to know what's been the most challenging part of building this, because there's so many moving parts, and especially the TPU waterfall, and like how did you do this, and what was the most challenging aspect of it?
Yeah, I would kind of I think there's 2 that come to mind. So the first one is related to the skipped slots, and I know probably any indexing provider for the chain is familiar with this problem, which is you want to show data as soon as it's available. And so we want to say, as soon as we got a slot, let's show it. Let's show all the data. Let's show that slot. Well, you may have to undo that slot, right? Because later it might get skipped, and kind of the data can change, and it can flip back and forth as the chain argues about whether a slot should be included or not, and people shift their votes. And so this kind of state machine, process that slots go through, where they become skipped and then they're unskipped and now they're optimistically confirmed and maybe then they got skipped. Again, modeling that and making sure we account for all the cases correctly and presenting a clean interface to it to this front end so it can display all that without doing a lot of gymnastics. It's quite difficult. And I think, that's the problem the RPCs have too, where, they want to insert things into a database really quickly so they can have real-time stats. But, then they need to figure out, okay, well, how do I undo all of this if it later gets revoted? And then how do I play back a different version of things as it happened? So that's kind of probably one of the main ones. Probably number two is really just getting the design right for this waterfall. I think it looks somewhat obvious as you view it now and you say, oh yeah, that is how you would show transactions moving through the system. But initially, when we were first building this, it really didn't look like this, right? We had a little console UI that has a few pieces of text, and we're trying to figure out as developers, well, where are we losing transactions, right? Where are they going? And a lot of the time you'll just look at metrics and say, oh, well, this metric counter increased, so maybe it was this part of the system. And kind of trying to figure out, and we work with a designer internally here in the Firedancer team who's very talented, kind of like work with him a lot to say, okay, how can we put this into a visual form that makes it very clear? So that's, something I'm quite happy with how it turned out. It was a little bit non-obvious to us in the beginning.
Absolutely, because turning all of this data into something that is visually understandable and kind of has that logical flow, especially for people that might not know absolutely everything that's going on in here, but still kind of have a general understanding. So you've also done an incredible job, and I know it's not the last iteration. So I'm very excited to see how it gets refined over time. And Matthias, did you have any other questions or?
Yeah, I just have one real quick question. And but first of all, I just wanted to thank you for building this amazing GUI, because it really helps the whole validator community to just find out what is the validator doing. Because before it was quite hard to extract the data out of the logs and out of the RPCs to see what happened when. And with this, especially with the timeline and the leader schedule, this is just great.
Nice.
I have. Yeah, you're welcome. Just have one real quick question when we could go back to the leader schedule for the duration times that we see. So the duration time is the time that took us to observe what happened, right? This was not the actual time that the validator took to produce the block, for example.
Yeah, you're correct. Yeah, and so this is all from the perspective of our validator. We don't know exactly how long that validator took on their own machine, and probably they would think they took 400 milliseconds, right, in almost all the cases. And if you look at our slots, we generally view ourselves as being pretty close to 400. There's reasons it jitters like this that generally to do with how we finalize when things are actually completed and so on. But so the other validators are going to be somewhat similar. Most of the time when it's showing long like this, it's really like a network delay. It's not actually that leader didn't do anything for 2 seconds.
Okay, gotcha. Makes totally sense. Thank you. And maybe because you asked if we have ideas for the future or stuff for this GUI, I could think of that validators would maybe like because on the overview page, you already show if we are voting and how much we're behind and stuff. Maybe if it would be possible and not such a hassle to build in maybe like a timeline for the votes, because with TVC upcoming, I'm pretty sure that some people will see, oh shit, I'm lagging behind with my votes pretty hard, and they won't get that much rewards. And maybe this would also be a cool possibility to see where it's lagging and stuff like this. But just an idea. I have no idea how complicated this would be.
Yeah, it's a very good suggestion. Thank you. We'll think about what we can do.
Nice.
One thing we know about the Firedancer team is that they really enjoy doing hard things, and we are entirely grateful for all of your hard work. And you've done so much building behind the scenes, and I'm very, very grateful for your time and energy, and taking the time to also come and explain it and make it a little bit more accessible to a wider audience. So thank you so much.
Great. Well, thank you for having us. It was wonderful to get to show our work and talk about it too.
Yeah, it needs to be out there and appreciated. And so hopefully your explanation can, really help people understand. I know I absolutely learned a lot. I spend a lot of time looking at this, and there's a bunch of things, even the expanded little buttons on the verify and different things. So thank you so much. Your time and big brain energy is so much appreciated.
Great. Thank you.